And welcome back, everybody. This is Yeti once again. We're going to knock out today the third installment of the land navigation series. So we've already gone over range beads, how to use those. We went over the military lensatic compass, and now we're going to visit map reading. Before we get started, if you are getting something out of this series, go ahead and like this video and share it with somebody. And go ahead and subscribe while you're at it. There's going to be a lot more content coming down the pipe. Okay, let's get started. So we've got a definition of a topographic map. It says without ever having been to a particular place and without talking to someone who has been there, you already know quite a lot about it with a map. A map is a graphic representation of the Earth's surface drawn to scale, as seen from above. It uses colors, lines, symbols, and labels to represent features found on the ground. However, the finest maps available are worthless unless the map user knows how to find them. Alright, topographic map description. First things first, reading a map is a language composed of lines, colors, and symbols. 5 basic colors are used for topographic maps. They include brown for contour lines, black for man-made features, roads, and trails, blue for water features, of course, green for vegetation, duh, red for highway and land grids. 2 minor colors are pink for built-up area and civilization, and purple for updated map information. Symbols are used to represent the natural and man-made features of the Earth. Lines show relief and elevation. It indicates the variations in terrain features and heights of natural features. Every map has margin information about the map. Very important. Maps come in 3 scale sizes, small, medium, and large, which affects the amount of area covered in detail that will be shown. So these scale sizes are basically, what you'll notice is the grids are bigger, smaller, etc. The bigger the grid, the more detail it's going to show, the more terrain feature changes that you'll see, the more precise you'll be able to get. Smaller the map, it'll show more area, which might be good for you needing to travel across a long distance, but the larger scale the larger the grids are, the more detail it will be. So if you're doing land nav and that sort of thing, it'd be to your advantage to have the large grids. A map is read for 4 basic kinds of information: direction, distance, position, and identification. Maps must be taken care of and properly folded for field use. There's a whole thing at the end of this for folding maps. There's like a whole science behind it. It's pretty fucking crazy. Also very neat if you actually learn how to do it and keep doing it so that you remember how. Next up, we'll talk about map margin information. So this is the bottom portion of a military map, topographic map. A map can be compared to any piece of equipment in that before it is placed into operation, the user must read the instructions. So we're talking about these being our instructions for the map. It is important that you know how to read these instructions. Honestly, when you first see it, it's like Greek. So that's why we have these sweet PowerPoints. The most logical place to begin is the marginal information and symbols, where useful information telling about the map is located and explained. All maps are not the same, so it becomes necessary every time a different map is used to examine the marginal information carefully. Alright, so at the top left corner of all USGS topographical maps carries the imprint of the authority responsible for the mapping. Neat. In the upper right hand corner is a complete quadrangle name, is the complete quadrangle name. The state is also given, as may be the county. Also included is the area covered and the type of the map. So this is basically your title. In the bottom right hand corner of the map is a key to roads on the map, map name and the state, date of the map, one of the most significant pieces of information available. That is true. You do need to know the date and how long ago that was. Some of the maps, at least maybe all of them, they'll give you sort of a estimation of the change for declination over time. So we'll go over that here in a little bit. Key to the roads is very simply just hardball roads, dirt roads, and differences between those on the map. And it also conveniently tells you what state you're in, which is pretty cool. Next is the quadrangle location shown as a black square superimposed on a state map. So that's literally showing you where this map is in the state. At the bottom center is the map scale ratio. That's the size of area covered and terrain detail. So this is when we were talking about small, medium, and large scale. So this is the scale of map, how much detail that you're going to see on this map, a little bit or a lot. How zoomed in is it is as seen from above. This also, FYI, matters what kind of protractor you're going to use if you're going to use a protractor. We'll talk about that probably in the next video. Distance bar scales show several alternative units for the measurement of distance. So those are those bars down there with the numbers. They're showing you what it looks like, distance, what it looks like in feet, kilometers, and miles. And it also gives you the contour interval. The contours are the brown lines. In fact, so this will give you basically the how steep each line is on the map. So showing circular rings for a hill, let's say, it's showing you basically how many meters, how many feet in between each line, so you can get an idea of how steep that terrain is mathematically. In the lower left-hand corner is the credit legend, a complex of information and the following. The magnetic declination. So this is probably the most important thing that's in the margin, I would just go ahead and say. It's going to go ahead and give you the conversion that you're going to need to go from map to compass, compass to map, be able to plan your route effectively and not get super duper lost. Okay, the star at the top of that declination graphic indicates true north, the direction of the north rotational pole. MN, the letters MN stands for magnetic north, indicates the direction of the north magnetic pole. GN is your grid north, the UTM or Universal Transverse Mercator grid. Additional information is distributed around the entire map margin. Only need to know items are circled. Okay, so you've got all of those circles corresponding to each one of these numbered items. So first up, you've got names for adjoining quadrangle maps in black, adjacent to corners and centers of the map sides. So what we're talking about here is there's clearly going to be other map sheets that all come together to wrap around the Earth in a nice tinfoil ball. Those names down there correspond to the other map sheets that are adjacent. So if you're going to walk off the edge of the map, you need to find, in the example here, the Dolores West map sheet down there in the bottom left-hand corner. Number 2, in red are the distances by road to the nearest towns. So you get a couple spots down there. In this example, down at the bottom, you see it says Dolores, the town of or city of, is 2 miles by road south. So helpful. Next item, number 3, is the spherical grid, latitude and longitude. Complete coordinates are given at each corner of the map. So basically, each corner, they're giving you your latitude and longitude so that you can match it to that method of navigation. Number 4, the UTM in black lettering with blue ticks, and the UTM grid is in kilometers. Cool. So number 4 there would be bottom right graphic, down in the middle, label number 4. You see it's got that 22 circled there. Alright, so we made it through the first segment. Fantastic. I know, PowerPoints are boring, but we got to lay the foundation, otherwise we can't get to the meat and potatoes, right? So if you actually want to know what you're doing with maps, go ahead and stick around. You'll learn everything you need to know, good foundation, and then we can move on to the fun stuff. If you do have questions that we didn't cover or you need explained, go ahead and drop them in the comments below. Okay, map scale. Map scale is the relationship between distance on the map and the corresponding distance on the ground. Scale is expressed as a ratio, right? That's where you get that funny 1 over 24,000 there. Shown graphically by bar scales marked in feet and miles or in meters or kilometers. Maps with a small scale, for example, 7.5 minute maps, are often called large scale maps because they show more detail by covering less area than large bar scale. So basically, when you are selecting a map to go somewhere, navigate, you need to think about whether or not you need more detail or less detail. I tried to talk about this earlier. This does a much better job of showing you pictures and going over examples. So basically, small, medium, and large is what we're talking about category-wise. So the small scale maps are 1 over 1 million or smaller. They're basically used for general planning or for strategic studies. So that's going to be your map on the wall of your big tactical operations center that you're looking at the whole country or half of it. Medium maps with scales larger than 1 over 1 million but smaller than 1 over 75,000. Used for operational planning. They contain a moderate amount of detail, but terrain analysis is best done with a large scale map. These are going to be your in-between one-size-fits-all maps. Large map scales of 1 over 75,000 or larger. These are used for tactical, administrative, or logistical planning, where you're actually driving around or trying to navigate by landmarks, stuff like that. So these are going to be probably the most useful for things like hunting and just general land navigation on foot. Alright, so here's the pictures that are going to bring all that together. So this is the medium scale topo map, the 1 over 150,000. It's basically some detail. You'll be able to navigate with it, but you'll miss a lot of detail, may get lost because of that. Bottom right, you've got your large scale topo map, 1 over 24,000. That's lots of detail. So you'll be able to see every nook and cranny. You can kind of follow on the map as you drop down the side of a hill and you pick up a swamp as shown. Now we've got your small scale map, 1 over 1 million. 1 million. It's very little detail. So again, this is going to go on your wall so that you can generally get a feel for the lay of the land prior to planning something. Right side, you've got your medium scale map, 1 over 250,000. That's going to be more detail than your small scale. And of course your large scale at the bottom there, like we said, for navigating by foot, etc. And of course these all correspond to each other if you hadn't noticed. So that's there for you to get a feel for which map you would like to select before you go to that area. And we're back to questions. Like I said, drop them in the comments. I'll answer them. And if you haven't already, please like this video. Next up, map symbols. Symbols are used to represent the natural and man-made features of the Earth. It is a map language that is simple to read and understand, but you must first know what the map symbols represent in order to understand, read, and speak map language to others. Here's some examples there. We'll talk about it in a second. Vegetation up first. Top to bottom, go with the woods there. Nice green patch. There's some pictures to help you out. Next to shrub, you got those green spots. Orchard, nice vineyard with some grapes. And a mangrove, which I've never seen before. Definitely an Asian thing. Submerged areas and bogs. This is the fun stuff. The stuff that slows you down. So we got the terrifying marsh or swamp. Not only is it slow and wet and gross, but it also has the wonderful animals of which I'm terrified. You've got submerged marsh or swamp. Okay, shade different. Wood marsh or swamp. Submerge wood marsh or swamp. You've got a rice field, never been. I like that it just says rice. Keep it simple, stupid. And then you got land subject to inundation. All right. Areas they can basically flood like crazy. Next, you've got rivers, lakes, and canals, all the blue on the map. Got your intermittent stream. You got your perennial stream, intermittent river, perennial river, small falls, small rapids, large falls, real scary ones, large rapids, perennial lake or pond, intermittent lake or pond, i.e. never there, if you weren't catching what the intermittent means. So don't plan a route based on an intermittent pond. It's definitely not going to be there when you count on it. There's a dry lake and a well or spring, not a sperm. Then you've got your dam and canals. Next up, man-made features and highway and land grids. So generally pink areas, gray areas are going to be your towns. Buildings are nice little squares. Schools have a flag. Church has the nice cross. Airports look like airports. Landing strip. Cemeteries. Pretty self-explanatory. The mine is an interesting symbol. Gravel pit. You've got highways. They're nice and bold to let you know they're hardballs. Road. Again, solid lines. Dirt road, i.e. possibly overgrown with hint of tire tracks. We've got a bridge, footbridge, which again, sometimes there, sometimes not. Things change. Trails, definitely never there. Just kidding. Sometimes maps are well marked. Sometimes maps are from 1983 though. Now you've got power lines. Railroads are pretty self-explanatory. And again, as always, if you have any questions, drop them in the comments and I will do my best. Alright, next we'll talk about contour lines. So we got a couple definitions here at the top left. First is contour interval. That's the space between the lines. So the contour interval is the distance between each contour line. The contour interval is found along the bottom edge, center of the map. Now we have intermediate contour. It's a brown line on a topographic map that represents a line of equal elevation. An index contour is a bolder, wider brown line that has the elevation value marked at various intervals as a part of the line. So what we're looking at is this, like the top right here, you've got the line down there at the bottom marked A. That's going to be an index line. It's going to tell you it's 700 feet, 700 meters, whatever it is. The intermediate contours are going to be the lighter brown lines in between the 7 and the 8, and then the space in between is going to be that contour interval. On this one it says 20 feet interval in between. So we can go through some of these examples here. So A, down in the bottom left, is marked 700 feet. And then we got letter B is 2 intermediate contours later. That's going to be 740 feet, right? So the interval is 20. It's right on the line, and so we're going to count 20 for that first line, and then 20 for the second line. And math's easy, 740 feet. Going on to Charlie, so being as though that's 740 at Bravo there, then going to Charlie, we go one more contour line, so that's another 20. So it's going to be 760, but C is actually in between two intermediate, right? So it's in that space. So when you have that and it's in the middle of the space, you go ahead and have the interval, right? Hopefully I didn't lose you, but back to B there, it's 740. You go to the next interval there before you get to C. That's going to be 760. And then because C is in the middle, we're going to have the next interval, and it's going to be 770 feet. And then finally D, that's going to be, we can choose to start at the 800 index line because that's easiest, right? So you start at 800, and then it's conveniently the next interval, right? So then it's a very simple 820 feet. So I'm sure you guys get the idea. It's pretty simple, except when you're hot, sweaty, tired, and you're cutting corners. And down at the bottom left, you've got basically just a little reference of what it looks like on a map compared to what it looks like to your eyeballs. Alright, there is a dimension to establishing position which does depend on map reading skills. This is the vertical dimension. On a map, it is referred to as relief. Knowledge of the relief of an area is extremely important to a wilderness navigator. The most graphic technique ever devised to show relief information is the contour line. If you were to walk a contour line, you would never go downhill and never uphill, and eventually you'd arrive back where you started. So the idea there on this graphic down there, it highlighted in red. So if you start there on one point of that red line, that's a contour, you'd follow that contour, if you could, perfectly by following your map, and you tried to walk that contour line. You wouldn't go uphill, you wouldn't go downhill, you would just make it all the way around the ridge line there and be back where you started. That's what they're trying to say there. So basically, relief is kind of the most complicated part of actually trying to read a map and plan a route and make decisions based on it. 'Cause sometimes you'll look at the map and you'll say, ooh, yeah, I can walk down this hill and into this little valley here. Problem is you read that wrong. You read it backwards, and it's actually uphill right? So it takes a little bit of extra effort to take a look at it, identify draws and spurs, so that you are reading the contours appropriately instead of backwards. And again, if you have any questions, drop them in the comments, and I will knock out some answers. Alright, on to terrain relief features. We'll blaze through this. We've got 5 major terrain features. You've got your ridge, hill, saddle, valley, and depression. We're going to show some pictures of these, so just stand by. We've got 3 minor, spur, draw, and a cliff, and then 2 supplementals, cut and fill. Now let's move on and we'll kind of actually see what these are. Alright, so the first one up is the ridge, right? And the fist here, you know, this is typically how you're teaching somebody these to memorize the terrain features. You stick out your hand, and the first thing you notice is your knuckles sticking up. So each of those knuckles is a hilltop, and then all of them together comprises that ridge. So it's got that nice graphic there on the bottom. Follow that hashed line, that's your ridge line. Next up is the hill. Pretty easy. You identify contour line that touches itself, right? It goes in a circle or some version of circle, surrounded by other circles. That is going to be, like we were talking about, our fist. That ridge line up there is full of those hilltops. So looking back at our fist, each one of those knuckles is a hilltop. There's a female anatomy joke in here somewhere. Alright, next up is saddle. Also female anatomy joke here. So back to the fist, you've got all those hilltops, right? Pick out 2 of those knuckles and look at the depression in between, or the space between the knuckles, sorry, and that grouping would be your saddle. Next we have valley. So this is pretty easy to find, usually water at the bottom of it. Definitely going to be a lot of contour lines on either side of it. Typically you'll see 2 walls of contour lines on either side, probably ridge lines on both sides as well. Next up is depression. This might be like a dried out pond or some bit of land that is below normal elevation. And if we take out our handy dandy hand, then we're looking at the palm area there that creates that little depression in the middle of your hand. Next up is spurs. So looking back at our saddle, the spur is actually nicely sloped terrain coming off of a hilltop or a ridgeline. That's typically where you want to climb the hill, by the way. Definitely not up a draw, which many would choose to do and be disappointed. Looking back at our handy dandy fist, we're looking at the finger lines coming off of the ridge. Those are the spurs. And next we have draws. These are the fun ones, right? These are where contour lines will come together. Typically there's water coming off of ridge lines through these draws. Where there's water, there's right? Vegetation. That's what makes these pretty rocky, wet, very thick vegetation. They're not places you want to travel unless you're trying to remain undetected or something like that. If you're going to climb a hill, definitely not a good space to climb the hill. You're definitely going to find a spur for that. And if we're looking at our fist again, the little spaces between your fingers, those are your draws. That should remind you. Next up is cliff. Your cliff here is going to be contour lines coming together into one line with the hash marks on the side there to show you that there's a bit of a drop off there. And if we're looking at our hand, the whole side of our hand there falls off, right? So that's going to indicate your cliff if you're trying to remember your terrain features. And lastly, you've got your cut and fill. And really we're talking about man-made features here. Building a railroad, you're going to blast and cut up the earth to put down a nice space for your rail line. So it's going to be your cut. And you've got those nice red arrows showing you where the cuts are. And then for the fill, that's obviously the backfill, right? So these rocks and everything that they've thrown in there to even out the terrain to throw down your tracks, that's going to be what that is. There to the right side, it shows the what it looks like on a map. And we have a nice graphic showing all the terrain features all at once, so that you can kind of point and test, right? Point and quiz. And again, if you have any questions, drop them in the comments and I will do my best. While you're at it, if you're getting some out of this video and if you stayed here this long, go ahead and like the video and consider subscribing for more content. I appreciate it. Alright, so now we get into the heavy stuff. So this is typically what people don't understand and probably need the most help with. So you can grab pen and paper if you need it, and then we can knock this out. It's really not that hard, but you need to understand what it is so that you can navigate without getting totally lost. All right, so what we're talking about is direction, right? So we're expressing direction. So you need a way of expressing direction that is accurate, is adaptable to any part of the world, and has a common unit of measure. Directions are expressed as units of angular measurement, and direction implies a reference point. The common reference point for maps is true north, and map direction is figured in degrees from that point. Azimuths. So the direction from one point to another, either on a map or on the ground, is called an azimuth. Azimuths are given in degrees in a clockwise direction. Since there are 360 degrees in a circle, an azimuth can be any number up to 360 degrees. East is 90 degrees, south is 180, west is 270, and of course north is 360. Maps are laid out with the top towards the top of the earth. True north, geographic north, and map north. The side edges of the map are the only lines on the map guaranteed to run true north south. So that may sound shade confusing. What you need to think about is, again, the earth being the ball, and then we're wrapping square papers around it, right? So obviously you're going to have angular problems, right? So that's what we're talking about here. And then your anchor points is what they're trying to say is these side edges of the map are the only ones that on the map that are guaranteed to run true north-south. The other ones could be angled, right? Moving on, the many north-south lines on a map give grid north. The compass needle points to magnetic north. Grid north and magnetic north usually have a few degrees difference. Neither points straight at the North Pole. That is called true north. All right. So true north, we're actually pointing to the North Pole, right? And then grid north and magnetic north, which is what we actually deal in when we're finding azimuths, those are not going to be pointed directly at the North Pole. With compass and map, you can know what direction you're heading. That's the whole point. So down in the middle, that's going to be your declination diagram. That's one of the big keys that you need to look at prior to stepping off on any sort of trip. You need to understand what the GM angle is, right? And that'll help you convert from azimuths that you get from the map, protractor maybe, also the degrees, the azimuth that you get from your compass. Okay, so 3 types of direction. There's true north, magnetic north, and grid north. Obviously, true north, we talked about that. That's literally any point in the Earth's surface pointing to the North Pole, right? And on the diagram, it's represented by that star, the North Star, right? Magnetic north. So this is north as it relates to your compass, right? So the direction to the north magnetic pole as indicated by the north-seeking needle of a magnetic compass. Magnetic north is usually symbolized by a line ending with half of an arrowhead. So if you look down there, MN in the magenta color, I think that is, it's got that half arrow. Grid north. The north is established by using the vertical grid lines on a map, symbolized by the letters GN, right? Grid north. Used for UTM grid by military and rescue teams for its accuracy and simplicity. So using a protractor of some kind, that's going to be how you're going to get angular measurements off a map so that you can navigate using grid azimuths, right? All right, GM angle. The angular difference between grid north and magnetic north. Why do we need to know all this? So that we can navigate using a map. The ground, we often forget the ground is important, and a compass. You cannot follow a grid north with a compass, nor can you plot a magnetic north with a protractor. To assist you in making the conversion from magnetic north to grid north, and vice versa, a declination diagram is placed on the map margin. Awesome. Remember the following. When using a map, use a protractor to measure grid bearings. Do not use the compass magnetic needle. When using the ground, use a compass to measure magnetic bearing. So, I mean, what we're talking about is when you're standing on the ground looking at a feature in front of you with your eyeballs, like a hill, then you need to use your compass, right? So that's what you're going to use to get your azimuth there, or your bearing. With grid north and the GM angle, you can find magnetic north. With magnetic north and the GM angle, you can find grid north. So you're going to be switching back and forth. Should you be maybe planning a route off of your map is usually what you're doing. So you'll lay your map out and you'll look at it, and you've never been to those places, and so you sit there and you plan a route based off of reading the map, like we said, identifying the relief features, figuring out which way is up and down, and then planning a route that's not going to kill you and that's going to meet your time hacks. And you plan that route using grid north, right, and grid azimuths. So you're using your protractor and you're finding these azimuths and you're writing them down. You're measuring the distance between points that you want to go to, and then you're going to write these down as part of your actual route plan, right? But then when you stand up and hold your compass out in front of you so that you can walk that azimuth, well, you can't use those same numbers because of these differences, right? So you'll have to convert from grid north to magnetic north so that you can walk each of those azimuths using your compass, right? So you can put your map away and you can walk each of these azimuths if there's no course corrections. That's the utility of what we're trying to do here, is you're planning a route on your map, writing down all these azimuths on a little sheet of paper, and then you're going to have to convert those using that GM angle so that you can have a bunch of azimuths converted to magnetic bearings so that you can walk those bearings, right? Hopefully that makes sense. If you're lost, just drop a comment. So, looking at the diagram, you've got magnetic north on the left-hand side, you've got true north in the middle, and then you've got grid north off to the right-hand side, right? So, the conversion we're looking to make here is going to require that we know that the GM angle is 24 degrees. And the way we get that is magnetic north is 14 degrees off of true north, right? So we're going to add that to the 10 degrees that grid north is offset from true north. So you add those two together, math's easy, 24 degrees, right? So now we have our GM angles. We're going to want to write that down somewhere. We're going to want to have that readily available so you don't have to keep pulling out the map legend. All right, so now we're going to talk about the actual conversion. So what we need to know is if we're going from a grid north azimuth to a magnetic north azimuth, which is, the scenario we talked about, route planning. If we're going to do that, we need to know whether we're going to add those 24 degrees or subtract those 24 degrees, right? So the answer is it depends, right? So you have to look at the diagram and you need to know whether it's adding or subtracting, and that's going to be based on this, right? So left to right, you subtract. Right to left, you add. Another way to express that is west to east, you subtract. West to east is least, so you subtract. East to west is best, so you add. All right, it's got a ring to it. When magnetic north is to the west or the left of grid north, magnetic north to grid north, we subtract, right? That's that left to right, okay? We subtract. Or the west to east is least. I like that. So grid north to magnetic north, you're going to add the GM angle, right? And the way this looks when you're actually converting, we talked about it last slide, was 24 degrees, right? So if we're going from that grid north to magnetic north, so let's say I got 100 degrees on the map when I'm planning my route, then I'm going to go from grid north to magnetic north, then I'm going to go ahead and add on this particular example. So I'm going to have to add those 24 degrees. So it's my actual magnetic azimuth that I'm going to walk is going to actually be 124 degrees. All right, so you guys get the idea. When magnetic north is to the east or the right of grid north, then magnetic north to grid north, you'd have to add the 24 degrees. And then vice versa, grid to magnetic, you're going to have to subtract the 24 degrees. All right, so you can see the top two sets. You've got magnetic on the left or the west side, and then down at the bottom you're going to have grid north on the west side or the left side, and then magnetic on the right side or the east side. So different maps are going to have different diagrams, right, depending on where you are on the Earth's surface. So don't know how much traveling you've done. Maybe all the maps you've seen are a certain way, but the planet's pretty huge, so maps are going to be different. So you're just going to have to take a peek before you actually step off on any sort of trip with any kind of map. So here's an example. Let's run through it. Pen and paper. We have our references at the top there. Left to right is subtract. Right to left is add. Okay. We've got our GM angle that we work out, which is 14 degrees plus 10 degrees is going to equal 24 degrees total for our GM angle. Okay, that's in the top right. From ground to map, so we're talking magnetic to map, right? So first, you measure the bearing of the landmark on the ground with a compass. All right, so what you're seeing is 49 degrees magnetic. Also, fun fact, when you are writing this down on index cards or piece of paper or whatever, while you're actually doing this in the field, you're going to want to annotate whether it's magnetic or grid every single time you write down an azimuth. Don't ever write 49 degrees and then just leave it be. You need to write 49 degrees M magnetic, or MN if you like. Same with grid. If you're working on your map, you're writing down all these azimuths for your trip, you need to be writing a G next to it. Next, the GM angle on the map is 24 degrees. We already said that. Number 3, so magnetic north to grid north, we're going to subtract. All right, now we referenced our little graphic at the top left there, kind of in the middle, and so we noticed that we're going left to right. Okay, so we're going to subtract. So it goes something like this: 49 degrees minus 24 degree GM angle equals what? Now it's going to be 25 degrees grid, right? All right, so the other way around, we're going from map to ground, or map to, or grid to magnetic, right? You measure the bearing on the point of the map with a protractor. All right, we're going to talk about that in, I think, the next section. I thought we were going to do another video, but we're going to do it in the next section. So you measure the bearing of a point on the map with a protractor. It is 25 degrees grid. So we look at our little handy dandy graphic at the top, okay? And we know that we're going from grid to magnetic, so we're going to add, right? The azimuth that we get is 25 degrees grid, okay? GM angle is 24 still, so we are going to add 25 degrees plus 24 degrees is going to equal 49 degrees magnetic. And this is what you're actually going to adjust your compass to read 49 degrees, and then you can step off on that azimuth. And it will be the same as walking the 25 degrees grid that you got with your protractor on the map, right? Does that make sense? So when you're planning a route, you're going to draw a line and say, ooh, what is this line? Using the protractor, it's going to tell you 25 degrees. Awesome. But then you convert it over so you can actually walk it with your compass. When you get done with that, you get 49 degrees magnetic. So you're actually going to walk 49 degrees, but if you were to follow yourself on the map, if you could do that with your little finger, then you'd be walking the exact same azimuth, but they're different numbers. Science. All right, example number 2, and then we will move on. Again, we've got our graphic up in the top left quadrant, and you've got your GM angle, which is changed on us, right? If you notice, the diagram is different in that bottom right-hand corner. GM angle has changed to 9 degrees, right? We've also got grid to the left of magnetic, or the west of magnetic. Okay, so we've flip-flopped things around. We're probably in Australia now instead of the good old USA. So from ground to map is our first example, right? So magnetic to grid. Number 1, you measure the bearing of the landmark on the ground with a compass. So perhaps we're aiming at that sweet hilltop with our compass, and we are reading 322 degrees magnetic. Number 2, the GM angle on the map is 9 degrees. Okay. Number 3, so magnetic to grid. All right. If we look at our graphic up at the top, we're going from magnetic to grid, which is right to left, right? So we're going to add. So 322 degrees was our original magnetic azimuth. We're going to add our GM angle, and we're going to get 331 degrees. Okay, so now if I want to draw a line on my map, maybe I'm lost and I'm trying to do resection, right? We could talk about that later. And maybe I'm trying to figure out like where I'm at on the map because I'm effing lost. I shot that azimuth and it's 322 on my compass, and I have to put that on my map. I can't just put 322, I have to convert it, right? So we just did. So now 331 degrees. So on my protractor, I'm gonna lay that down, find 331, draw a nice line, and then I'll use a straight edge, boom, knock that out. And then I can find on that line where that hilltop is, right? And then I can follow that on back to where I am. Pretty cool. So we'll talk about all that later, don't worry about it. Now we'll move on to map to ground, right? So we're going from grid on your map to magnetic on the ground. right? So number one, you measure the bearing of a point on the map with a protractor. All right, that point happens to be 331, and that's 331 grid, because we're writing the G next to our numbers. Okay, number two, GM angle is still 9 degrees, hasn't changed on this map, right? Side note, please check the date and make sure that you're not looking at a GM angle from 1983 and it being 2022, because it's going to be a shade different, and you'll be able to look up those changes if you get inquisitive enough online. So still 9 degrees. Go back to the number three. So grid north to magnetic north, we're going to subtract 331 degrees minus GM angle of 9 degrees equals 322 degrees magnetic. We're going to write that M next to it so we don't forget, right? And you're going to put this on your compass and start walking, or whatever you're going to do with it, right? All right, so it's simple enough. You just have to keep things straight, keep your paperwork neat, and label your azimuths. All right, so that was kind of heavy. If you have questions, like I said, drop a comment and we'll work it out. We'll do math together online. All right, cool. So next we're going to talk about the protractor. All right, this is generally what you use in the military. It's even got a GTA number right there for you, so that you can order these if you're in the military. If you're like a super high speed specialist who wants to learn land navigation, you can go ahead and order these. You don't know how to do that, shut up. All right, so number one, with a protractor, the map does not have to be oriented. All right, cool. So you don't have to lay the map down and use the compass, line it up with the edge, and then move in a circle until you find north, and then you lay the map down and you create a shrine. You don't have to do that, right? You have a protractor, so you can just lay the map down and go to work, right? So number two, it is used to calculate direction from map to ground, right? So grid to magnetic, by converting the protractor grid north to a magnetic north for the compass. Number three, it is used for the following: plotting azimuths, which is what I've been talking about, plotting your position, I think I mentioned that once, and then plotting UTM coordinates. I'm not going to mention that note because it's confusing. Of note, there are certain compasses like the Sunto M3. Is it Sunto? Yeah, it's a Sunto. All right, so Sunto M3, it has a feature on there where you can adjust in the compass itself the declination, and then you no longer have to convert. You just go grid to magnetic, magnetic to grid, and you don't have to worry about the conversion anymore. It's a pretty neat feature, so I picked up one. They're very useful. But if you're using your standard compass or standard lens-added compass, stuff like that, you're going to need to learn how to convert the GM angle. It's really not that hard. Don't be a gear do and just go out and buy stuff just so you don't have to do math. It's really not that hard. And before I move on, just the features of the protractor here. You start with the kind of crosshair in the middle with the dot. So that would be the middle. That's what you're going to line up on a map. Let's say that you have a grid and you put a little dot there on your map and you're wanting to find an azimuth from that point. That's where you would line up the protractor. You would put that protractor dot right on top of your dot on the map, and then make sure it's straight, obviously, parallel, perpendicular to the grid lines, and then you use the inner square with the numbers, right? And that would be your degrees. So if you can look at those numbers, at the top is going to be 0 or 360, right? And to the right, you're going up, 5, 10, 15, 20. And then on the left-hand side, you're obviously going the other way around the circle. So north is 0, east is 90, south is 180, west is 270. You guys see that? Okay, the numbers on the outside of that, those are mils. Those are the two angular units of measurement, right? And they're both on there. You can use either one. Mils are generally used for artillery fire in the military. That's why they're there. Now, for the three triangles, this is just those small, medium, and large maps, right? So if you've got a map that's meant for land navigation and orienteering, stuff like that, you're probably going to be using that huge triangle, 1/250,000 or something similar. If you're looking at the map inside of your tactical operations center, right, like some officers are walking around and stuff, the map on the wall will likely be one of those 1/100,000, right? And then normal people who walk around in the woods, they'll have a 1/50,000 map, and that's what you get, right? If you'll notice on these triangles, each of those lines are marked 0 to 10 or 1,000, right? That's how you're measuring distance on the map, right? Because each of those grids on a military topographic map, each of those grids are 1,000 meters by 1,000 meters, right? You'll start at the bottom left hand corner of your grid box, and you'll put that, or the 0, 0 lines, you're going to set that at the bottom left hand corner of the grid box, and then you'll slide it over, and then you'll peek at the spot that you want to see on that vertical line, and then you draw a little dot. That's how you find a grid, right? And of course, each of those numbers corresponds to, like the 1 is 100 meters, 2 is 200 meters, on and on. If you don't get it, it's fine. We'll do a more hands-on class later about how to actually plot points and stuff like that. This is all the baseline background information so that you can know what the equipment is and what it's for. All right, we're going to get a little hands-on here with the protractor. So number one, all right, so we're talking from map to ground, right? So from grid to magnetic. So number one, you're in the thick woods and cannot see any landmarks, but you decide to go to a hill, which is marked A on the map. Number two, with protractor aligned with the grid lines drawn on the map and the center of your protractor aligned on your map position. That's where you are, right? That's what I was talking about, keeping the protractor aligned with the grid lines, parallel and perpendicular. Just making sure it's square, right? So set it where you are, and then you're drawing a line on your map, right? Or you're holding a straight edge over the top of your protractor, and then you line it up with that hilltop, right? That's what you're really doing. You see that the azimuth is 29 degrees or 520 mils. Number four, you convert this to magnetic azimuth and put this on your compass. That's where you do your little conversion, like we talked about before ad nauseum. Then you'll walk that new azimuth. All right, so if you have any questions, go ahead and drop in the comments, and then we'll work through it, man. All right, moving on to orienting the map with the landscape. So we talked about if you have your protractor, it's not necessary to orient your map. Now we're going to talk about how to actually orient your map, which is that reference. You can see the picture there in the top left. He's trying to orient his map to terrain features, right? That's called, your technique number one is you're orienting to true north. Identify several landmarks on your map and on the terrain, which, by the way, may be super hard, and you might not be able to do that, okay? Imagine standing in the middle of the woods. You can't see anything around you. There's no landmarks, just a bunch of trees. Number two, visually orient the map landmarks with the terrain landmarks. So you're fiddling with your map until you get what you see in front of you to match what's on your map, right? The map is now oriented to true north sides. Technique number two is magnetic north. So with the compass and the map, you can do this technique. So number one is you lay your compass on the magnetic north line of the map. You rotate the map and the compass together, so you're holding it firm together, right? You rotate them until the compass bearing reads 0 degrees, magnetic north. Now the map is oriented to magnetic north. Pretty simple. And then you're getting those nice little pictures down there to show you how to do that. All right, so the third technique is to find the magnetic declination value in the map margin. Okay, example is east 11.5 degrees. Number two, place the compass edge on the edge of the map, north and south line, with the front of the compass facing the top of the map, obviously. Number three, rotate the map and compass together until the north arrow is 11.5 degrees east of the black index line. Note, the black index line is aligned with 348.5 degrees. The map is oriented to true north. Okay, technique number four. When your position on the map is known, you can use this technique. Number one, select a terrain feature on the ground that you can find on the map. Example, the hill. Number two, with the compass, sight the azimuth to the hill, which in this case is 295 degrees from your position. Number three, align the compass edge through the hill and your position. Number four, rotate the map and the compass together until 295 degrees is aligned with the black index line. The map is oriented to magnetic north. Yeah, they do have nice graphics. So those are the different methods. If you sit down and fiddle with it, you'll 100% understand what they're talking about. Again, if you have any questions, drop in the comments and I'll try to answer. Next up is map information, and we're going to talk about distance. The relationship between map and ground distance is the function of a bar scale. The bar scale looks like a small ruler and usually has 3 to 4 bar scales: feet, miles, meters, and kilometers. The ability to determine distance on a map as well as on the Earth's surface is an important factor in planning and executing safe, practical routes. So this graph down here, the bars, you're going to use them when you're planning route distances. Like for instance, if you're taking a convoy somewhere, or you're driving somewhere, you can take out a piece of paper and start making tick marks along your route, turning your paper to keep it in line with the road and all of its curves and everything. And you'll get a million tick marks depending on how long your trip is. And eventually you'll be able to count them up as it relates to that graph, whether you want to look at kilometers or miles or feet, and you'll have an estimated distance. The map scale of 1 to insert number means that 1 unit of measure on a map is equal to that number of units of the same measure on the ground. So because of that, a map scale of 1 over 25,000 means that 1 unit of measure on the map is equal to 25,000 units of the same measure on the ground. So this means on a map, 1 inch would be equal to 25,000 inches, or 2,083 feet, or 694 yards on the ground. Also, on a map, 1 centimeter would equal 25,000 centimeters, 250 meters, or a quarter kilometer on the ground. A map scale of 1 over 100,000 means that 1 unit of measure on the map is equal to 100,000 units of the same measure on the ground, just like the last one. So of course that means that on a map, 1 inch would be equal to 100,000 inches, 8,333 feet, 2,778 yards, and 1 3/4 miles on the ground. And of course, if that's true, then on a map, 1 centimeter would also equal 100,000 centimeters, or 1,000 meters, or 1 kilometer on the ground. I'll spare you guys the last example there. It's the same exact thing. You guys get the idea. Alright, so this slide is going to drive home that point. Now you get a nice picture to look at. Basically, the navigator is using centimeters on the map, measuring a distance 10 centimeters, and then converting that using the map scale. So this one is 1 over 25,000. So the equation goes like this: 10 centimeters times 25,000 for the map scale equals 250,000 centimeters, which is a useless figure, but 2.5 kilometers is useful. Alright, map information position. Finding one's position on a map in the usual sense, such as the intersection of 2 compass bearings, is more a matter of compass technique than of map reading skills. But it is possible to locate your position on a map without a compass by land features and map association. It is impossible to be totally lost. Finding your location is a process of narrowing down the options until you can determine a point on a map. I'll caveat that with you can totally get lost if you lose your map and your compass. Boom. Now, by determining the lay of the land and finding prominent features, then relating them to your map, the narrowing down process will not take long. Landmarks can be anything that you recognize as being on the map. Classically, these are hilltops, but you could use the intersection of 2 roads, of buildings such as a power grid substation, the abrupt edge of a ridge, the edge of an island, and the bend of a trail. Anything that you can recognize as being on the map that you can see. There is a second dimension to establishing position, which does depend on map reading skills. This is the vertical dimension. On a map, it is referred to as relief. We talked about this with contour lines. Knowledge of the relief of an area is extremely important to the wilderness navigator. Yeah, we'll skip ahead. We read these when we were talking about contour lines. Navigation is not about finding yourself after you are lost, although that's what happens sometimes. Navigation is about keeping track of your position as you move away from a known point. As you move, you have to remain cognizant of the terrain you are leaving, of the terrain you're passing, and the terrain that's coming up. In case you weren't tracking thus far, navigating is a pretty difficult task, very taxing. It shouldn't be taken lightly. In the Army, for example, when patrolling, you have to have at least a few people paying attention to navigation. Generally got like a squad leader type person who's got a map and who's tracking the unit's movements, making decisions on route planning, etc. And then you've got maybe a sergeant, team leader who's up front on point, and he's using a compass. They're also keeping a pace count while they move. Everybody's keeping a pace count. And you've got assigned duties: primary compass man, alternate compass man, then you've got your primary and alternate pace man, and all these people are there to help the squad leader keep track of navigation. Alright, now we'll talk about identification. Identification of significant features, both natural and man-made, is partly a matter of knowing language and maps. One category of map language is lines. In addition to showing contour relief, lines are used to portray roads, trails, railroads, power lines, and drainage features. Another category of map language is composed of various picture symbols. A third part of the map language is color. If part of identification is knowing the language of maps, the rest of the problem is interpretation. What is the relationship among certain lines, symbols, and colors? Reading contour lines is literally reading between the lines. Contour lines represent the shape of the terrain only at specific intervals. The user must be aware what lies between may be quite different. There could be rugged terrain, vertical bluffs, or deep ravines that might not be shown. A river may be drawn somewhat straight on the map, but the terrain's actual river meanders, with many curves, turns, and wide and narrow banks. And of course, contour lines on a map do not show you everything. Scan the landscape between the lines. Alright, so main idea here is that the in between the contour lines could be, like in this example, huge gash in the earth, right? So to summarize briefly, the map is going to show you through the use of lines, color, and symbols what the earth in front of you looks like. Back to questions. If you have any questions, drop them in the comments and we'll move on. Alright, this section is all about map identification. The differences between a topo map and aerial photograph, and then the actual land features, what it looks like. So they'll show you a few views and give you an idea what the land actually looks like. So on the left you've got the topo, and then on the right you've got what it actually looks like in person. Again, you got on the left the topo version and what it looks like in real life on the right. Alright, now you've got two different views here, right, of the same location. So you've got view 1 in the top in the northern sector, and then view 2 in the south. And we're about to go through a bunch of photos that's going to show the different views. Feel free to pause the video to be able to soak it in. Alright, so this is view 1 looking south. And those are the different points on the map you can identify if you look back. This will be view 2 looking north. And then again, those are the different points of interest you can find on the map if you pause and move back and take a look. Alright, so here's both views. Map is turned upside down so that you can look from view 1 towards the point 2, and then there's the picture what you're actually looking at with the topo on the left. Now we flip the map back around and we're looking from view 2 towards photo 1, which you're actually seeing in front of you is on the bottom right, and then the map is on the left. Alright, now this is both views, what you'd be seeing from each view, and the topo on the left. And if you have any questions, just drop them in the comments. And now we'll go through a little map folding and map care. Maps should be correctly folded. Maps should be folded to make them small enough to be carried and still be available for use without having to unfold them entirely. After a map has been folded, it should be placed in a folder for protection. This will prevent the corners and edges of the map from wearing and tearing easily when opened. It is hard to navigate accurately with dirty, grimy, wet, or damaged map. Take care of your map, it'll take care of you. Most maps are printed on paper and require protection from water, mud, weather, and tearing. Get a map case. Whenever possible, a map should be carried in a waterproof packet to prolong its life. Like I said, map case. Waterproofing maps to include a Ziploc bag. So understand that when you throw a map in a map case or a Ziploc bag or something like that, you'll definitely need to anchor that map to the map case. It's going to shift around and stuff like that, so you'll need to mark it with the northing and easting so that you can tell where the map needs to be shifted before you make any sort of measurements with PROTRACTOR or anything like that. If it is necessary to mark a map, use light lines so they can be erased without smearing or smudging. Talk about pencil marks on the actual paper map itself. If the margins of the map must be trimmed, note any marginal information which may be needed, such as grid data or magnetic declination data on the back of the map. You may have to, in the middle of the paper map, you might have to draw in pencil all the grid marks so that you can reference those if you have to fold it to where you can't see the lines that are already on the map, etc. Special care should be taken of a map that is being used in any situation, especially in a small group. The mission may depend on that map. And of course, as with any special equipment for any sort of patrol or team or anything like that, all members of the group should know the map's location at all times. And map folding. So lots of techniques for this. I'm actually going to do a separate video because this video is getting too long anyway. So stay tuned for the rest of the land navigation series and you'll pick up on the map folding as well. Super cool techniques. It's definitely going to be worth a watch. Alright guys, that brings map reading to a close. That'd be the third video in our land navigation series. So if you made it this far, you're obviously a serious student. Stick around, there's going to be more videos, including we're going to put the classroom skills that we're learning to use. So we'll do some stuff in the field. It'll be a lot more engaging. So stay tuned for that. And if you're getting some out of the series, please do like this video. Let me know how I'm doing and that you want some more content on the same subject. And do consider subscribing so that we can grow the channel. I can drop videos more than once a month.